Welcome to the unit on mass transfer as part of the NPTEL MOOC on transport phenomena in materials. This lecture is about the overview of this unit. So what is mass transfer about? So it's about the balance of mass, and we have already done a derivation earlier in the chapter for fluid flow, what is called the continuity equation. And in what way is this chapter mass transfer different from what we have done earlier? So the equation that we have derived earlier goes as displayed here: dou rho by dou t plus nabla dot rho u is equal to 0. In this case, rho is the density and u is the velocity of the liquid. Now when we look at mass transfer, we are considering many constituents, such as, for example, the domain consists of elements A and B, or species C and D, and so on. So what does this quantity rho imply? In what way is it related to the constituents that are present in the domain? And the velocity u, what does it refer to? The velocity of which constituent is to be taken? So these are the questions that we will have to answer when we embark on this unit on mass transfer. The simplified form of the equation for the continuity is given here, which again is for a situation where we have an incompressible fluid. So we will how we bring about the mass transfer and conclude that the continuity equation will still hold. Only thing is that we need to give definition to what u means and what rho means. So the continuity equation, as a matter of fact, was using the continuum approach as opposed to the atomistic approach. In other words, the domain is deemed to be consisting of material that is uniform, whereas in mass transfer we are going to be conscious about different constituents and species that are present in the domain. So in other words, we should not lose track of what are the constituents that are present, because they do play an important role, and we need to retain the details of these constituents that could change. What we mean is, in case of reactions, we could actually lose some constituents and form some constituents as a part of the process. The rate at which some constituents are created and some constituents are destroyed is part of what mass transfer is going to help us understand. So often there is a misconception about the use of the words composition and concentration. So let us first define what is composition. Composition of a mixture is defined by the nature of the phases present and by the quantity of each constituent in each phase. In other words, both the information about the phases as well as the constituents of those phases are to be specified when we say the composition in a particular domain is specified. And composition can be expressed in terms of titers or concentration. You can see that concentration is a way to express composition, but it's not the same. So what is titer? So how we proceed to define composition in terms of titer, I will just briefly give you. Titer is basically a concept where we want to determine what are the compositions of the solutions that are in consideration, and a solution is said to be titered when its composition is known. Titer is a dimensionless number. It is a ratio of the quantity characterizing a constituent to the same quantity characterizing the solution. Nature of the titer is to be specified. That is it specified, the quantity that is characterizing the constituent, is it specified in terms of its mass, or in terms of its moles, or in terms of its volume? So it's a volume titer, or a molar titer, or a mass titer that we need to specify when we want to determine the composition of a solution. And it can be expressed either as fractions or ratios. Naturally, fractions can also be expressed as percentages. So let us take the first titer, called mass fraction. So mass fraction is typically specified using Wi, where I is the constituent we are interested in. So there could be many constituents that are part of the domain. Mass percentage is simply 100 times the mass fraction, and we define mass fraction as follows: Wi is equal to mass of the constituent I divided by the whole mass of the mixture. This is very useful when we want to create alloys from pure elements. So usually in metallurgical practice, one would specify mass fractions very commonly while giving the composition of a system. Mole fractions are defined as follows. They are usually designated using Xi, and mole percentage is nothing but 100 times the mole fraction, and it is defined as Xi is equal to Ni by sigma Ni. That means the number of moles of the constituent I divided by the total number of moles of all the constituents put together. We can also define one more tighter going by the quantity volume. Volume fraction is denoted usually using phi I for the constituent I. Volume percentage is 100 times volume fraction, and volume fraction is defined as follows. It is equal to volume of I in mixture divided by total volume of the mixture. And very often one may confuse this volume fraction with so-called partial molar volumes in a single phase mixture. One should not do that, because in the discussion that follows we illustrate how these are very different. So we can say that composition can be specified using a titer. Composition can also be specified using concentration. Concentration can be given in terms of molarity, that is number of moles of the constituent I divided by the number of liters of the solution made. This is a popular measure used in chemistry to determine the concentration of a solution. Molality is another measure defined as number of moles of I per unit kilograms of the solvent. So it's only the denominator that is different. And mass concentration is defined as kilograms of the constituent I per unit volume of the solution, where the volume is given in terms of meter cube. So you can already see from the definition that mass concentration of a solution that contains a single constituent is nothing but the density of that particular constituent. Now comes a question. If you mix 50 ml of water and 50 ml of ethanol to form a solution, will the solution be 100 ml? The answer is no. The solution will be less than 100 ml. The reason being that the water molecules and the ethanol molecules will attract each other, and the total solution will be less than the sum of the individual volumes that we have given. So which means that we need a different perspective to see how we actually take these concentrations, not from the pure constituents, but what happens to the solution. And that is the thermodynamic perspective to mixtures. And this provides us other means to specify effective composition. Effective as in means how does it affect the chemical potential, which actually leads to the driving forces for the atoms to move around and change the composition. So partial molar properties come of great use when we want to describe what happens to the volume when two constituents are mixed to form a solution. So let us take, for example, the situation that we have just discussed just now. V prime is the extensive variable, namely the total volume of the solution. V is the molar volume, that is molar volume, that is the volume per mole of the solution. Va is molar volume of pure A. Vb is the molar volume of pure B. And we are considering a solution of A and B. So we now determine the partial molar volumes using new symbols which have a bar on top. Va bar is partial molar volume of A in the solution, and Vb bar is partial molar volume of B in solution. And we define the molar volume as a sum given as V is equal to V bar A XA plus V bar B XB, where XA and XB are mole fractions of A and B in solution. So in using this definition, we can now see how does it actually help us in determining the volume of the solution given the individual volumes of A and B. So let us consider this following construction. So let us consider the volume of 1 mole of the solution of A and B. So we plot along the y-axis the volume of the solution, and on the left hand side of the axis is pure A, the right hand side is pure B, and along the x-axis we are varying the atom fraction or mole fraction of B. And let us assume that the volume of 1 mole of solution of A and B follows a curve like that. If it is an ideal solution, you must be having a straight line, but it is a curve because it has some negative interaction, negative deviation from the ideal solution behavior. And where it touches the axis, we have the symbols VA showing that it is a molar volume of pure A, and VB showing that it is molar volume of pure B. Now at a given composition XB, we can now see how we actually define the so-called partial molar volumes of A and B in the solution AB. So what we do is that we draw a line vertical from the composition that we have chosen, and where it cuts, we could draw a tangent. The tangent is then going to intersect the axis at two different points, and these are V bar A and V bar B. So these are the partial molar volumes of A and B. So our definition that the volume of the solution A and B, which has a composition of B as XB and composition of A as XA, which is equal to 1 minus XB, because XA and XB, their sum is 1, then the volume of the solution is given by V bar A into 1 minus XB plus V bar B into XB. So we have now seen how the deviation from the ideal solution behavior, or a direct mixture of the two quantities, is not giving us the value of the parameter V, the volume, for a given solution. So let us formulate how we can approach other parameters of thermodynamic importance using the same concept. So let us look at how we arrived at these partial molar volumes first of all. So we treat the V volume as a function of pressure, temperature, and all the number of moles of the constituents, assuming that there are C number of constituents for this particular solution. So we can expand the volume as a function of Pt N1 up to Nc. In that case, a small change in the volume of the solution can be expressed in terms of the differentials of the pressure, temperature, and other parameters as follows. dV prime is equal to dou V prime by dou T, keeping pressure and the number of moles constant, into the differential dt, plus dV prime by dP, keeping temperature and number of moles constant, to dP, plus a summation of terms, and each term basically for each constituent, dV by dN, keeping pressure, temperature constant, and all other moles constant except the one for which the subscript is given, into dN, the constituent that is under the term. And this actually helps us in expanding this dV prime relating to physical parameters. That is, the first term in blue relates to the thermal expansion coefficient. The second term relates to the isothermal compressibility. The third term relates to what we have just now discussed, namely the partial molar volume. So now we can formally define the partial molar volume of the component K. So it is defined as follows. Okay, you can see from here it is defined here. Vk bar is equal to dou V prime by dou Nk, keeping pressure, temperature, and all other number of moles of the constituents constant except the kth constituent for which we are defining the partial molar volume. And notice the bar on top of the volume, that indicates that we are talking about partial molar quantities. Notice that we are differentiating with respect to the total volume and not molar volume on the right hand side. So partial molar quantities are defined at constant temperature and pressure. This is very important because later on we may come across quantities where what is kept constant could change. However, partial molar quantities are always defined with temperature and pressure kept constant. Now we may expand the concept of partial molar quantity that we have defined for volume to any other thermodynamic parameter, and we choose the parameter to be arbitrarily B. We may think of that B to be, for example, Gibbs energy, which will be quite useful in a moment from now. So we may expand now dB prime, that is the extensive variable B. dB prime is equal to m into dt, plus n into dp plus sigma over all the constituents 1 to c b bar k dnk, which means that the partial molar B for component K is then defined as follows. You can see from here it is defined as partial derivative of the extensive variable B prime with respect to the number of moles of K, which is matching here K, keeping temperature and pressure constant and all other number of moles also constant. Now you can clearly see that this relates to the chemical potential what we would have come across in thermodynamics. So if you were to see the quantity B to be say Gibbs energy G prime, then this is an expression that we are familiar with from thermodynamics. dG prime is equal to minus SdT plus VdP plus sigma of all the chemical work terms that are given by mu k dnk, where mu k is a chemical potential. And partial molar Gibbs energy is nothing but chemical potential, because when we look at this term and keep temperature and pressure constant, naturally there is only one term on the right hand side, which is basically the chemical potential, and keeping all other number of moles of the constituents constant except for the kth constituent that we are defining this for, we see that the definition is available here readily. Mu k is equal to G bar k is equal to dou G prime by dou nk, keeping temperature, pressure and other constituents number of moles constant. So whenever there is any change in the partial molar quantities, we now need to see how does it actually help us connect. So there is a concept in thermodynamics that we make use of, namely the fact that order of differentiation does not matter. This is because most of the thermodynamic functions that we are dealing with are continuous and well-behaved functions, and their slopes are not zeros. So that is the reason why we can go ahead and assume that the order of differentiation does not matter for thermodynamic functions. And in such cases, we can actually show that dG bar k, that is the differential of chemical potential of the constituent K, is equal to minus S bar k dt plus V bar k dP, which means that not only is this expression without the bars and the K, what is coming directly for unary systems, we can actually keep the subscript and put a bar on top, and it is now applicable also for partial molar quantities. And because we already noticed that the partial molar Gibbs energy is nothing but chemical potential, we can actually write d mu k is equal to minus S bar dt plus V bar k dP. That is for the kth species or kth constituent that we are defining this quantity. So here we come across an important parameter, fugacity. We will actually spend few minutes to understand what is fugacity and later on generalize it to a quantity called activity, and we see that it's a very good measure of determining how different constituent elements are playing a role in the evolution of the composition of the system. So fugacity is nothing but the tendency of a constituent to escape from a medium. So naturally it is defined for a gaseous phase, and fugacity of a constituent I in a condensed phase is defined by the fugacity of its vapor at equilibrium. And the measure of the influence of the constituent on its chemical potential in the solution. Fugacity basically gives you how the constituents are influencing the chemical potential in the solution. And the chemical potential, as we have seen earlier, is defined here. Once more we recollect that it is defined as dou G prime by dou Ni, keeping pressure, temperature constant and all other constituent number of moles also constant. So here is a small tour of fugacity. So let us look at the differential of the chemical potential in terms of dt and dP, where the coefficients are minus Si and Vi. Now we would like to integrate, keeping the temperature constant, going from pressure Pi naught to Pi, and you can clearly see that the left hand side can be directly integrated, it's a state function, and on the right hand side, because we have kept the temperature constant, then we do not have the term coming from the entropy here, and we only have the VdP term, and therefore we are basically writing the integral as it is. And if I were to be in a solution that is an ideal gas, then we can actually substitute Vi to be RT by Pi, where Pi is the partial pressure of the ith component and substitute to get the integration, giving us on the right hand side RT ln Pi by Pi naught. This is how we can actually see when the partial pressure of any constituent changes, then how the chemical potential is affected. So we have seen that we have used the ideal gas equation while integrating the right hand side, which means that when we want to do this integration, we need an equation of state, and for real gases sometimes we may not have it handy. So in such a situation, what we are going to do is as follows. So what we are going to do is that instead of the partial pressures of the constituent elements, we actually use a quantity called Fi, which is the fugacity of the constituent I. So the expression here is identical to what we have seen earlier, RT ln Fi by Fi naught, where Fi is the fugacity of the constituent I in the mixture and Fi naught is the standard fugacity of the constituent I. And we know that all real gases tend to behave as ideal gas as the pressure goes towards 0. We can say the following, namely Fi by Pi tends to 1 as Pi tends to 0. So the relationship between fugacity and the pressure is given as follows. We can see from the right hand sides of the two expressions, RT ln Fi by Pi is equal to integral going from Pi to Pi naught Vi dP. And this has to be evaluated with respect to the limit, where as the partial pressure of the constituent I goes to 0, the quantity Fi by Pi tends to 1. So the fugacity is completely defined by the following rigorous relationship, namely RT ln Fi by Pi is equal to integral from 0 to Pi Vi minus RT by P dP. Now using the same concept, fugacity, which we can apply now to the condensed phases and define a quantity called activity. So we define activity as Fi by Fi naught, which is fugacity of I in mixture by fugacity of I in its standard state. So when the constituent I is in gaseous state, it is very common to take Fi naught as 1 bar. When I is in condensed state, it is convenient to choose the pure compound I as standard state. When the pressures are very low, we can actually assume that the fugacities are nothing but the pressures only. So Ai is equal to Fi by Fi naught, which is approximately equal to Pi by Pi naught, and which is equal to the ratio of the vapor pressures of I over mixture by vapor pressure of I in its standard state. If I is in a solute dissolved in a solvent, then the activity can then be defined as the ratio of the concentrations. So Ai is equal to concentration of I in the mixture divided by the concentration of I in its standard state. And for metallic solid solutions, we define the chemical potential expanded in this form: mu I is equal to mu I naught plus RT ln Ai, where Ai is the activity of the species I in the solid solution. And we expand this activity to include the mole fraction using the activity coefficient. That is, Ai is equal to gamma I xi, where gamma I is the activity coefficient and xi is the mole fraction of the constituent I in the solution. Now gamma I, the activity coefficient, if it happens to be 1, then we can say that the solution is exhibiting a Raoultian behavior or an ideal behavior, and the solution is supposed to be exhibiting Henrian behavior or Henrian behavior when the gamma I is constant, that is, when the activity is proportional to the mole fraction and the activity coefficient is a constant, then we can say that the solution exhibits an Henrian behavior. These two actually are very useful in making some derivations as we go along in this chapter. So what are these constituents we are talking about? So in mass transfer, we don't use the word atom every time or even molecule. We refer to the constituents as species. That is, unlike atoms, species can mute. That is, consider the example of oxidation of carbon to form carbon dioxide or carbon monoxide. So with some oxidation, the carbon monoxide can become carbon dioxide, which means that the species can change their form. And the balance equation is not directly written for a given species because they actually can change during a reaction. So which means that the balance equation is written for atoms of each type. So we need to keep track of how many different types of atoms are participating in the domain that we are considering, and write balance equations for all those atoms. And in case the system contains ions or ionic species, then in addition to atoms, we also need to have a balance equation for the total charge. Sometimes vacancy is also treated as a species. The reason being that in multi-component alloy systems, when the diffusivities of different species are different, we may need to actually invoke vacancy as one of the species so that the equations are actually more easy to handle. In this unit on mass transfer, the organization of topics is as follows. We come to the solid state diffusion as one important chunk in this unit, and these are usually discussed in the context of physical metallurgy. We do discuss about convective mass transfer, and that is usually when flux is more important to arrive at overall solute balances. Here we draw a parallel between the heat transfer coefficient and mass transfer coefficient, the so-called Nusselt number and Sherwood number, and we then use those analogies to talk about flux. That is, borrowing concepts from heat flux, we write what is mass flux and then use that to do the overall solute balance. We also need to talk about convective mass transfer when fluid flow is playing an important role in the evolution of composition changes in our domain. We also need to bring in reactions, because very often we have situations in metallurgy where the species can change their form. So reactions with a generation term are going to be important. What we mean by the generation term will be clear if we have kept the derivation of the governing equations till now in mind. The last term on the right hand side is a generation term, as we would see also in this particular chapter shortly. When a species is generated or consumed at a location because of a reaction, then we need to use the reaction terms to arrive at the balance of solute. We also have some concepts of solute redistribution that will be important. Usually this occurs during partitioning when a phase transformation is taking place. Examples of such situations are solidification. That is, the composition of the phases that are in equilibrium are different across the interface, and that would bring in a situation where the solute has to have some partitioning across the interface as the interface moves. And we can actually also deal with those situations under the ambit of mass transfer, use the same governing equation and arrive at solutions that we would actually discuss in chapters on solidification or welding in the typical metallurgical textbooks. Some background concepts that we will require as a part of this chapter are as follows. We need to actually revise the balance equations that we have written for a control volume in the earlier units on heat transfer and fluid flow. We will have to revise what is called a chemical equilibrium from thermodynamics. We will have to bring in the reaction equilibrium concepts from thermodynamics. We will actually use these concepts directly to write some expressions in the equations that we need in this chapter. We also need to bring in some solution thermodynamics concepts. We will not make it complicated by going to very difficult models. Simple models such as regular solution model or ideal solutions would suffice. We can build on our earlier learning of deriving balance equations and solutions from heat transfer and fluid flow to make this module on mass transfer easier. So with this we come to the end of the overview of mass transfer.